Good afternoon, welcome everyone to the Colloquium. Today's speaker is Michel Mayor, who is Professor Emeritus at the University of Geneva and is famous for having observed the first extrasolar planet, together with his colleague Queloz. Michel stayed for most of his scientific career in Switzerland, where he obtained his doctorate in 1971 at the Geneva Observatory. Later, he has spent various sabbaticals at ESO in Chile and in Hawaii. He has been a full professor in Geneva from 1988 onwards. Michel's main research interests include exoplanets, instrumentation, statistical properties of double stars, globular cluster dynamics, galactic structure, and kinematics. His achievements are too numerous to review here, given that he has more than 700 publications. Suffice it to mention that, as said before, Michel made the first observation of an exoplanet orbiting the star 51 Pegasus in 1995, and afterwards he has made further first observations, like first discovering a planet in an habitable zone. Michel has been awarded for his scientific work a great number of prizes and honors, like the Gold Medal of the Royal Astronomical Society, the Albert Einstein Medal, and very recently the Wolf Prize in Physics. Moreover, he was made Knight of the French Légion d'honneur in 2004 and is Foreign Associate of the French Academy of Science. Enough of the praise, let us now hear about the current state of research in this very rapidly developing field.
Yes, because many things appear in that field during the last 22 years. And I will try not to cover everything, but try at the end of my talk to focus on the problem of the discovery of the smallest planet, and more important, if it is rocky planet in the habitable zone of stars. I will give only few slides of introduction to the field, and then after we'll discuss more carefully. So as you know, that the solar system is only one star among something like 200 billion of similar stars. The Milky Way is something quite similar to that one. And maybe you can notice here, you can notice small patch of pink colors. It's not stars, evidently. It's giant molecular clouds. And these kind of clouds are, we will see later, the origin of stars and planets. But maybe we can do a small historical back discussion. And contrary to what is commonly believed, that astronomers do not believe in other extrasolar planets until 1943. In fact, this is the estimated number of planetary systems in the Milky Way during the first part of the 20th century. And you have big names of astronomy, Sir James Shapley from Harvard and so on. And you see, during the first part of the 20th century, the general common idea was that you have no other planetary system in the Milky Way, or maybe some exceptional case. And suddenly the ideas changed in the early 40s and jumped to 10 to the 10, 11, and so on. And today, the observation will confirm that we are in these things. And also, what is very interesting to this plot, so you see that you are allowed to change your mind by a lot of order of magnitude, by a factor several million. Okay, so you see, the ideas was absolutely not in adequation with movie and books on fiction and things like this among astronomers. So, giant molecular clouds. So maybe several of you know this. It's the Orion Nebula, relatively close to us. It's a big cloud of something like 10 to the 5 times the mass of the Sun. And sometimes you have some special process creating a collapse of the cloud and creating a new generation of stars. In 1995, the Hubble Space Telescope looked in detail few stars in front of the Orion Nebulae. And you see these stars here. It's just few among many, many. And all of them have a small disk of dust and gas around. And this is the origin of the formation of planets. Because this was the missing point during the first part of the 20th century. Nobody understood where it was possible to have this kind of nebulae. Because the classical theory proposed by Jeans was that you need a very close encounters between two stars to have the formation of a nebulae. And the probability to have this kind of event is so bad, so low, that was the reason why we were not expecting as a planetary system. But after this, people discovered that, in fact, accretion disk, this kind of nebula, are absolutely a byproduct of the formation of stars themselves. So a priori, we can estimate that almost all stars should have one or several planets. Today, several techniques have been proposed to detect extrasolar planets. I will discuss only the two first ones. So the Doppler spectroscopy is my own hobby. And you have the planetary transit. And you have quite a lot. Direct imagery is already working, not so easily, but OK, we have some first discovery. Astrometry, almost nothing. Gravitational lenses, it's only maybe 10 or 20 objects have been discovered by this technique. But in the future, maybe space mission will provide, I don't know, thousands of extrasolar planets by this technique. And chronometry was used to discover the companion of the pulsar in 1992 already. So probably the most interesting discoveries done during the last 20 years was a diversity of planetary systems. Okay, until 1995, we had only one example, the solar system, and we have some kind of special feelings that maybe every planet should have the same hierarchy with, in the central part, some rocky planet, and in the external part, some gaseous giant planet. And this was absolutely not true. And this is a summary of the discoveries done during the last 20 years. This is the logarithm of the mass. This is the logarithm of the semi-major axis, but you can have some translation in terms of period. So this object has a period of about 10 days. This is 1 year, maybe 10 years here. And this is the mass of the Earth. Here's the mass of Jupiter. It's 300 times the mass of the Earth. And you see that the mass and periods of planets are incredible, covering the full. Okay, this is only because we don't have the techniques to detect this object here, but you see that you have a huge amount of planets with period of only a couple of days, some of them with low mass, some of them with only three hours, so extremely tight orbit. And evidently, we have also some kind of normal gaseous giant planet at several AU. So this is the first point we have to explain the diversity, discovered diversity. And the different colors with, okay, here you have the list of technique. The blue are objects discovered by the technique of spectroscopy. Transit Okay, the probability is much in favor of short period for the transit, so it's the reason why you have so many green points here, and so on. So, in one word, what is a Doppler spectroscopy? If you have the star, you have the planet orbiting around, you cannot see the planet, but you have a small pull, gravitational pull, and if you measure the velocity of the star, you can detect a small Doppler effect. Evidently, it's not so important as you see before, because the planet is extremely small, so the Doppler effect is quite small, and presently we have a sensitivity to detect Doppler shift at the level of 10⁻⁹. So this translates to something 0.3 meters per second. So it's interesting to detect this kind of a certain planet, but later we will see it's not enough to detect Earth-type planet in normal habitable zone position. So I will not discuss a lot the past, but all the stories start 22 years ago. We have built with some colleagues a new spectrograph. Implement is below, is linked by a fiber to the telescope. This is an old telescope, it's not so important. And the sensitivity of the spectrograph was enough to detect this first motion, so this is velocity versus time or phase. And so the surprise was to discover an object with almost the mass of Jupiter, but with a period of only 4 days. And nobody was expecting a gaseous giant planet with 4 days. And the reason was very simple, that in the disk, accretion disk around the stars, in the middle of the disk you have only silicates and metals, and the mass of silicates and metals is absolutely not enough to build a gaseous giant planet. You need to agglomerate ice particles, and evidently ice particles do not exist so close to the star, so it's not easy to understand the formation of a gaseous giant planet on so short. You see, it's 25 closer to the star compared to the distance between the Earth and the Sun. So this was the shock, and just to have a cartoon of that, in fact, you have the star, like it was the Sun, a star very similar to the Sun, and you have to imagine a Jupiter planet orbiting very close, and you have to understand what is the mechanism of formation of such a system. It's very interesting to see that the theory was already existing, but nobody read carefully the papers, because in fact it was a paper on the engulfment of small galaxies by big galaxies. If you have, for example, normal big galaxies like our own one, and you have a small galaxy like the Magellanic Clouds, you can study the dissipation and the formation of the engulfment of these small galaxies, and what is the time scale for the migration of this. But in fact, the same theory applies to extrasolar planet, and this was published quite soon after our own discovery. And here, just to have an image of what happened, if you have a disk of dust and ice particle, and outside the ice line, where, in the external part, it's maybe 5 astronomical unit, you form a small protoplanet, and then the mass of the protoplanet will induce some density wave in the disk, and the reaction of the excess of mass will create some shrinking of the orbit of the planet. And the time scale could be extremely short, and immediately after 95, the question reversed, how to stop the migration. The phenomena was apparently too much efficient, and so it's still an open question. But it's evident, it's Newtonian dynamics. It's a phenomena existing. Happily for us, this migration do not exist for every long time. Evidently, after when you have the disappearance of the accretion disk, and you see after a few million of years, the disk of the accretion disk disappear, and after we have a stable dynamics of the solar system or any planetary system. Today, we have access to a huge near-infrared interferometer at 500 meters in the north of Chile on the Altiplano. It's something like 60 dish of 12 meters, and you can combine all the light measured by all these dishes to have a huge sensitivity, angular sensitivity. And 2 or 3 years ago, some colleagues have a look with you can have something like a baseline of something like 14 kilometers between the different dishes, and have a look with the interferometer of this very small cloud where we knew that we have young stars in the middle, T-Tauri stars. And then after what was the point? So this is the image of the central star, young stars, with the accretion disk around, and you can see the details of the formation of planetary system. Okay, so this is a completely new domain with the possibility to have a look on the formation process of planets. So apparently things appear very clear that if you have a star, you have the disk, and you have formation of planets out at some distance, and then after you have migration, and it looks evident that you should have the angular plane of the planet should be almost parallel to the equatorial plane of the star, like we have in the sun. Then after, we have the possibility to have some direct measurement of this effect, and this refers to what is called the Rossiter-McLaughlin effect. If you have a star, you can imagine that the star is rotating, and you have a planet crossing the disk of the rotating star. So here you will stop the light coming from the star in your direction, and after in the other direction, as a net result that the absorption light of the star will change a little bit during this phenomena. So if the orbit of the planet is parallel to the equatorial plane, you will stop the light coming in a small fraction of the light coming in your direction, so you have an excess, apparent excess of if the star is moving away, and the reverse on the other side. So this is typical signature you are expecting. If the planet will be moving on the other side, retrograde orbit, the signature will be something like this. If you have a situation like this, you have only a small part on these things here and the larger one here, and so on. So you see that you have access by this technique, very simple technique. In fact, you have access directly to the relative orientation between the orbit of the planet versus the equatorial plane of the star, and you can check if it's really prograde or retrograde. This is a real planetary system. This is a normal Doppler motion due to the pull of the planet around the star here, and at the time of the eclipse, of the transit, you have the normal signature we have described just before. You see, this is a normal situation. But more and more, we have discovered quite a lot of objects like this. So, in fact, contrary to what it was expected from the migration, in fact, you have additional dynamical processes. And we have worse. This is a cartoon, it's not the observation. We have several objects where the planet is orbiting in the reverse side, so it's retrograde orbit, and sometimes with very inclined orbit. So, and this is evidently absolutely not compatible with simply the migration described before. So the classical explanation that when you have several massive objects, you have what is called quasi effect. So you have some perturbation from another object in the system, able to change the inclination of the inner object. So just to see that the dynamical evolution of the system are quite complicated. So myself, I was more involved in Doppler spectroscopy search, and the present we have two similar spectrographs able to achieve that kind of measurements. Here we are using something like 6,000 absorption lines together. So evidently, because we don't have so many photons when you are measuring a star. So you have to concentrate all the Doppler information diluted in the spectra to get only one quantity, the velocity. So this can be done by some kind of cross-correlation technique. And so we have carried out and it's continuing, a very long survey in the southern sky because we have our interesting instrument in Chile. And this is some kind of historical graph. Here you have the mass of the planet detected as function of the time, starting with 51 peg here. Okay, then you see the huge number of extrasolar planets detected by the Doppler spectroscopy starting from that time. But the second interesting feature is the fact that the lower mass detected during the last 20 years decreased from the mass about of Jupiter to about the mass of the Earth here. So we have better instrument, better strategy of measurements, so we start to approach the mass of rocky planet. Just one, at the present time, we have maybe almost 4,000 planets detected. I will not show every of that. It's only one example. One very unexpected feature so was the fact that we have discovered a lot of multi-planetary systems. This is one example, a system with, here you have the velocity versus the time. You have 2,000 days, something like this. The red dots are one night of measurement or one measurement. And you see you have a cloud like this. And okay, we have some suspicions that you have at least one Kepler motion, Kepler here. But when you look in details, in fact, you have 7 planets. It's the superposition of 7 systems. So at present time, it's a very standard feature to have a lot of planets. And once again, with something completely unusual, a period of 1 day, 5 days, 16 days, and with mass of few times the mass of the Earth. It's a very interesting system. You see, the central part is very packed. So immediately you ask, is it stable or not, such a system? And in fact, you start to do some integration, long-term integration of the system, and you discover it's not stable. Then after you take into account the tidal interaction between planets, it's a little bit better. And then after you have to take into relativistic correction to have a really stable system for a long time. So you see this kind of, the nature produces very strange objects like this. So this is a view of the survey done during several years, the mass versus period. You see the hot Jupiter. Jupiter will be at 300 times the mass of the Earth, and a couple of days of period. In fact, they are not frequent. The hot Jupiter-type planets are not frequent. Most of Jupiter-type planets are really with long period. But what the second point, very interesting, is that this huge population of what is called super-Earth and Neptune-type planets. planets with mass between 1 and 10 times the mass of the Earth. In the solar system, we do not have any planet in this range of mass, but apparently this is one of the most frequent type of planets with only a few times the mass of the Earth. After you can estimate the number or the fractions. If you look, for example, between 3 and 100 times the mass, you in a period of less than 1 year, you already have about half of the star with planet. And evidently, you have to take into account we are not observing here where we have many more planets. So okay, what is the fraction of stars with planet? Maybe 100% minus a fraction, I don't know. But okay, all stars would have planets. Next step, we have discovered that a lot of stars have short-period planets. So the probability to have a transit, so an eclipse, the fact that the planet will cross the disk of the star is very high. It could be at the level of few percent. So if you measure a lot of stars, you should have a lot of systems like this. And if the planet crosses the disk, you will have a small drop of the luminosity, and it's directly a measure of the size of the planet. So the Doppler spectroscopy gives access to the mass, and this technique gives access to the size. So this is the first object discovered in 1999. So we have discovered a planet with a period of 3.5 days. Few colleagues at Boulder with a very small telescope, because it was a bright star. Exactly at the good time, saw the drop of the luminosity by a little bit more than 1%. Then they repeat the measurements the next season with the Hubble Space Telescope, and you see the quality of measurement you can have when you are out of the atmosphere. So this was the beginning of a very exciting technique. And the most impressive diagram we can see is the galore of discoveries done by the by Kepler space mission. Here, this is the radius of the targets observed by Kepler space mission, as function of the period in days. And you see, I don't know, it's 4,000 planets discovered. The idea is very simple. You have a small telescope looking a small part of the sky during three years, continuously, and having one measurement every few minutes. Then after you have, I don't know, few 100,000 light curves, and by software you are looking for some kind of periodic signal. And at the end, it's this kind of diagram. Okay, here, this is the sensitivity of the technique here, and you can see some colors here. And for example, the red colors refer to planetary system with 6 planets, 6 different planets orbiting the same stars. So this is absolutely a fantastic technique, and with the capability to detect objects with radii smaller than we have for the Earth. This is unit of Earth, planet, so all these objects are smaller than the Earth. Anepili, you see, this region here is empty. And the satellite died and will not continue to explore this domain. Here, this is the same kind of plot with the radius versus the temperature estimated at the surface of the planet. And Anepili, the habitable zone, the zone where you can expect that the water will be liquid, is almost empty here. So this is one of the future difficulties we will encounter. Presently, we have a second, the first HARPS instrument, spectrograph I showed, was in Chile, in southern hemisphere, but Anepili, The Kepler target was in the northern hemisphere, so we have been obliged to develop a copy to implement at Canary Islands at La Palma. And, for example, we put most of our observing effort to try to study the domain of small planets. This is Earth-type planet, twice, 5, and so on. So it's a couple of times of the mass of the Earth. And you see that all these objects have been discovered. K is one Kepler, but you have also objects discovered by different techniques. And we see that up to 5, 6 times the mass of the Earth, we have a rocky composition similar to the Earth. And it's only above this limit that we have some kind of Neptune-type planet with an envelope and so on. So presently, we are trying to complement the measurement done by Kepler, because if we want to start some physics on the formation of this object, we need to have both quantities. So the idea is very simple. You have the star, you have the orbit, and you have the planet in front will give access to the radius of the planet, and then after you have some kind of orbital phase, so you have some kind of access to the thermodynamics of the atmosphere to see the cooling of the atmosphere. Then afterwards, the planet disappears, you have a drop of the infrared luminosity, so you have access to the temperature of the atmosphere of the planet. And what is probably the most interesting thing, that the atmosphere of the planet is transmitted through, the luminosity of the star is transmitted through the planet atmosphere. So if you compare the spectrum here and here, when the planet is behind, in fact, you have access to the physics of the composition of the atmosphere of the planet. And this is one first measurement. Here you have the flux versus the wavelengths. The squares, the black square are referred to measurements. And you have different kind of models with different composition to compare. Okay, still not very constrained. We see here, because every model are almost at the same place here, and where you have a real significant change, we are not really constraining. But this is the direction, and this domain will have a huge development in a couple of years, because you need a lot of photons, because the difference between both spectrum it's very small, so you need a lot of photons if you want to have access to this kind of composition. Another interesting point here is this is the luminosity curve. This gives access to the radius of the star, of the planet. But here you have the drop of the infrared luminosity gives the temperature of the planet, and this is related to the phase, orbital phase of the planet. So next step, we would like to detect Earth analogs, and just to give an example of the difficulty of this. This is a real image of the sun, okay, in H alpha. So it's very evident that you have this outer convective zone with matter going up to 1 kilometer per second, some other part going down to the same velocity. You have spots, magnetic activity, and so on. And this is the Earth. So we would like to see the transit of the Earth in front of the star similar to that one. Or you can see, we try to see the pull or the wobble of the velocity due to the presence of small planet. It's okay, the mass of the Earth is 1/3 or 300,000 smaller than the mass of the Sun. So this is a difficulty to search for this kind of. So at the present time, we are not limited by the precision of instrument. we are mostly limited by the stars themselves, by this kind of phenomena I showed. So this fact that we are not measuring a very simple object with a lot of convection, magnetic activity, and so on. So probably the next step will be to understand a little bit better this kind of phenomena. And presently, I have one colleague here of Geneva, but also with several colleagues from different places, having built a very small telescope to measure continuously the sun, but with some clever device to have the sun as a star. So to not see the disk, but to mix all the light, and to use after the HARPS spectrometer we are using to see what is the velocity of the sun. So what we can expect. This is the sun, and these are the reflex motion of the sun due to Mercury, 1 centimeter per second. Okay, the Earth is 9 centimeters per second. So you see that we are a factor 10 smaller than the present precision we have due to the jitter, due to the magnetic activity. So at the present time, we have not the possibility to detect this kind of objects. What are the cause of this jitter of the velocity? The first one is the change of the apparent velocity of the sun due to what is called the solar magnetic cycle, 11 years. So you see that you have a small apparent change of the velocity of the sun. If you look in detail, a small season here, you see that you can see the rotational period of the sun here, with few meters per second here. When you analyze a small part here, on a full night, in fact, you see that you have a change due to what is called the granulation. The fact you have this a lot of convective zone activity. And if you are looking a small fraction of here, you can see what is called the oscillation, the acoustic mode of the sun with a few minutes of period. So all these effects are limiting the precision we have. Okay, for the sun, we have a two-dimensional image. For the star, we have only 1 point. So the idea is how to use our measurement of the sun to try to improve the precision we have on the velocity of stars. So this is not the Rossiter-McLaughlin effect, but it's a quite similar effect. Voila. Okay, when you have a spot, you have a star is moving with a spot. In fact, you have a change of the velocity, of the apparent velocity of the star, simply because we are blocking part of the luminosity of the star. If you analyze the measurements done of the stars, this was done by these people having this small telescope. In fact, you can see all the harmonics of the rotation of the sun with something like 15 days and so on, all the same. So we would like to use this kind of experiment to understand how we can apply this to other stars. So this is one picture of the surface of the sun, where you have the convective zone here. So here, hot matter going up, and here, cold matter going down, and so on. And it's only, when we are speaking about the velocity of the sun, it's just only the mean of the velocity of all these atoms. If you analyze the velocity line by line in the solar system, we have 660,000 lines in the visible. In fact, you see that small lines have this kind of apparent velocity, and saturated lines have a different velocity with a difference of 600 meters. It's simply because the formation level of the different absorption lines is not the same for all these lines. So we can try to use this physics to correct for the phenomena of the convective zone. And at the present time, we are building in Geneva a new kind of spectrograph, much more sensitive, much higher, to be implemented on the VLT, it's the 8-meter telescope in Chile, and with the goal to try to improve a little bit the precision of the velocity we can have, and with the goal of 10 centimeters per second. So I will move to some more, comment dire, positive results, because it looks a little bit depressing, this is what I said before. So in Chile, some people have a small telescope and was looking for transits of relatively low mass stars relatively close to the sun. And they discovered a star with 2 or 3 planets 2 years ago, 1 or 2 years ago. And then after they applied to get time, observing time, with the Hubble Space Telescope and other telescope and ground-based or not. And 2 months ago, they published a paper with 7 planets orbiting this small star. So just what happens? This is the luminosity curve of that star called TRAPPIST-1. And you see that you have transits here, but they are absolutely not periodic. And it's very complicated to analyze. Happily, the length of the different transits is different from one star to another one. And you discover that you have several stars, 7 planets orbiting the same star. And if you are looking in details, you see that you have, okay, I will show in another slide that you have some of these planets in the habitable zone. Oh, okay, I will not read every value here. The period is 1 day, 2 days, 4 days, 6 days, 9 days, 12 days, and so on. So it's a very packed system. It's a delight for dynamicists because you have 5 different resonances. It's a system with a lot of resonance between the different planets. And you see that the mass is less than the mass of the Earth, 0.8, 1, 0.4, 0.6, 0.7, and so on. So this is all rocky planet with some of them in the, I don't know where, yes, temperature here. You see you have some of them with temperature almost not too different from the temperature we have on the Earth. Okay, what we have to notice that the mass of the star itself is 8% of the mass of the Sun. So it's a very weak nuclear reactor. The luminosity you see is extremely small compared to the luminosity of the Sun. So it's the reason why the temperature, despite the fact that the planets are so close to the star, that the temperature is not too big. We have some problem because probably probably all these planets are tidally locked. So all these systems are synchronized. So you can imagine that all these planets have one face looking always in direction of the small star. You have at some phase you have a huge flux of particles. I don't know if it's a good place for life. This is an interesting diagram where you compare the solar system with the TRAPPIST-1 planet, and it's not the unit of length here, but the flux. So the flux of the Earth is 1, and you see that you have several planets with flux close to the flux receiver of the Earth. So this is present, and the advantage of this system that it's only at 12 parsec. So among the very close objects we have, so with the possibility to do follow-up measurements. This system is relatively weak. The star is relatively weak. So with our spectrograph, we do not have the possibility to measure the Doppler effect. But happily, the tidal interaction between the different planets is such that you see that the timing are changing. So if you are looking one planet, we are expecting that you have a very clock, a precise clock with periodic transit. But when you have two planets, you start to have some interaction. And if you have several planets, evidently, and you see that you have sometimes the transit is in advance or is delayed and so on, and with an amplitude of, it's in this case, half an hour or things like this. And you have the possibility to use this information to get the mass of the planets. So, what is the central question? Is life a cosmic imperative? So in the sense, if you have the good condition, maybe they are very numerous, temperature, mass of the planet, and so on. If you have all these numerous conditions, evidently we always have all the atoms we need. This is not the difficulty. So do we have the emergence of life? Nobody knows on that. This was proposed by Christian de Duve, this form of interrogation. In the future, we'll have a space mission. Okay, you have Kepler now, but you have two small missions before, TESS and CHEOPS. But in 5-6 years, we'll have another mission called Plateau 2 to be launched by ESA, and with a special sensitivity to planets in the habitable zone around solar-type stars. So this is the space aspect. How we can dream to detect life on extrasolar planet? You have several possibilities. One will be, for example, to try to detect the equivalent of the vegetation. So if you have chlorophyll or other kind of similar molecules, in fact, you have a specific feature of the reflectance of the vegetation as a function of the wavelengths or polarization. So if you have simply the possibility to get images in different colors and doing also polarimetry, you can maybe detect the possibility that you have some photochemistry related to some kind of molecules. You see, all these kind of molecules have some similar behavior in terms of wavelengths and polarization. Obviously, if you do not have a planet with only vegetation, but you have only 20% of ocean and 80% of vegetation, the curve will not be so fantastic and it will be more difficult. But just to have a comparison, if you have only an ocean, it will be like this here. So this is one possibility to see if you have the development of living species. What was proposed 30 years ago, I believe, was to search for the very important feature of ozone at 9.7 micron. So here you have the spectrum of the Earth versus Venus and Mars, and you see only the Earth have this strong feature, ozone here. But evidently it's 9.7 micron is not a very easy domain, and you have to go in space and stop the light of the star. And this was the origin of the two very important space mission called Darwin in Europe and TTF in the States, and both missions have been cancelled and maybe will be developed again in the future, but for the moment we do not have this possibility. So what we can have in the future, you have the James Webb Space Telescope in 1 year, 6.5 meter telescope in the space, and we will have maybe the possibility to detect not ozone, but the molecule O2 by transmission. So transmission spectroscopy is what I showed before, that what the star, the planet is in front of the star on behind. You can compare, and you will have the ability to detect the excess of oxygen in the atmosphere. But you see, it's only few times the mass of 10⁻⁵. So, okay, it's a very small feature, spectroscopic feature, but it's not impossible. In fact, we have measured the reflected light of 51 peg exactly at the same level. Only the velocity is not the spectrum like this. So we already have the capability to approach this kind of precision. And why we are interested in oxygen? Because oxygen is a special element with a tendency to form oxides. And it's completely unusual to have 20% of oxygen like we have in the Earth, because we need to have a source to replenish always the quantity of oxygen in the atmosphere of the Earth. And the only efficient mechanism to produce oxygen is biotic chemistry. So it's only because we have living organisms on the Earth that we have 20% of oxygen. Okay, we have other processes, but not efficient enough to accumulate and maintain 20% of oxygen. So in some sense, it's maybe not enough, but it's a very, very strong indication of life if we can detect this kind of oxygen abundance. So what kind of dream we have? So this is the Hubble Space Telescope, 2.4 meter diameter. The James Webb to be launched in 1 or 2 years with 6.5 meter. And the next project, okay, not decided to do, is with this telescope with a high definition space telescope with a much larger dimension, something like 12 meters or diameter. On the ground, we have, because we can do a lot from the ground, and also in transit spectroscopy. And this is a project in development in Chile, and to be implemented in a few years, with a 39-meter diameter of telescope. So I don't know what is the size of the room, but it's probably larger than this room for the size of the telescope. You can see the car, the van here. So, and this will be implemented in north of Chile. This is the present set of 4 8-meter telescope, and the 39-meter will be on this mountain here. Okay, and I believe it's finished. Thank you.
Thank you very much. First question to Alvaro.
I'm here. Suppose you finally find a place where they're making life. Probably once you have life after a while, you will have intelligent life in some places. I say probably, that didn't say how probably. Certainly not in this planet, but maybe in others. And if you have such a place a few parsecs away, what's the hope of directing your radio telescopes there to listen to their television stations? How many orders of magnitude is that into science fiction?
Okay. This is, okay. When I was mentioning the possibility of life development, in my mind it was only unicellular form of life, very simple form of life. So at least already we have this question. But this is, during 3 billion years on the Earth, we have only very simple organisms like this. And then after you have multicellular organism, and intelligent life appear in the very last moment. So this is much more ambitious question, and this was promoted already from 1959 by Giuseppe Cocconi, and then after he was working here, and Phil Morrison, and this was the origin of the experiment SETI, to listen. And then after you are facing the question, okay, probabilities, you have planet with a good condition. I believe we have plenty of planets with a rocky planet, good distance, and so on. It was a question 20 years ago, 30 years ago, but today we are absolutely sure that we have huge amount of good planets in terms of life. And then after you start to enter this completely unknown domain, and what is the probability of life development? And this is not a problem for astronomers, but for biologists. And then after you are jumping to intelligent life, and after you are entering in still another domain of sociology. How long will be the duration of intelligent life? This was a typical question in the 60s at the time of the Golden War, of the Cold War, that people was a little bit pessimistic on the long-term evolution. So, and in any case, okay, I've been attending myself in some conference on SETI experiment and things like that, and I was always a little bit disappointed because people say our best estimations that we should have at least 10,000 similar civilizations in the galaxy. So what is the probability to detect them? Okay, after you arrive, that you have some value of the detection probability. But the first question, how do you have an estimation of 10,000 civilizations? It's completely unknown. So it's not a critic. It's not a critic because the instrumentation developed by these people are extremely clever. They analyze a huge number of wavelengths, try to analyze if you have something unusual embedded in this kind of signal and so on. But what is the chance? What is the probability to detect something? I don't know.
That was not my question. My question was technical. Is it possible, if you have not very far away a planet like ours, to listen to the radio stations?
No, I don't. Okay, I don't have the answer, correct answer, but I think I don't know. I don't believe we have the sensitivity to do it.
That SETI makes no sense.
No, it's depend if you have a signal sent by a large radio telescope in a specific direction. This is the basis of SETI. It's not the TV background, because you have a problem related to your question. It's the luminosity of the Earth in the domain of television wavelengths, at least a few years ago, was very high. The Earth is very bright in this domain of wavelengths. Today, with cable, it starts to decrease. But I believe it's only if you have directional beaming that you have a chance to detect them.
So it's only if they are trying to talk with us?
It's
only if they are trying to talk with us?
Or sending message. But also you have the question, okay, the typical wavelength is 21 centimeter, because it's wavelengths where the interstellar medium is transparent and so on. But are you sure that other people will use the same technique to communicate if they have the need to do something similar? And for example, I don't remember the name of the man having invented the maser, Nobel Prize. Okay. And he said, oh, if I would like to try to communicate, I would prefer to use an infrared laser. So we don't have only guarantees that some intelligent life in some place will use 21 centimeter.
Yeah, probably intelligent enough.
To try different technique.
Okay, you showed several two-dimensional diagrams of the size of the planet versus the rotational period. And you did also say that, of course, these distributions are very much biased by the detection technology, certain combination. So presumably one can make an efficiency correction to these maps. So divide out the sensitivity in these two dimensions and then have the primordial distribution. How does it look like when you go towards Earth? Does it fall? Is it flat? I mean, so how does the efficiency corrected two-dimensional distribution look like?
I will try to
take out the observation bias from all these techniques.
Okay, this kind of diagram here, here are not suffering from your comments, because here this really observation by the same technique as with radiography technique, and it's only one technique, and then after you can compare, do some modelization to see the sensitivity we have as a function of the mass and the period and so on. So this plane is relatively unbiased. Okay, you see the probability of detection here is 20%. So you can compare this. Here it's 100% in this region here. So here it's 0 here. So and we are using this kind of plot to compare with people doing some formation of planet. You have different teams trying to do some formation of planet.
That if I would correct that, it does strongly increase towards small planets. So
yes,
the corrected map would we say there are many small planets of around a year or so. So there are probably, because if I have to divide this density by your efficiency, I see that there are many small planets with periods,
oh yes, yes.
With periods of 1 year.
The probability of increase quite a lot with what you are decreasing the mass. And unhappily, okay, it's not completely true because right now we have the Kepler detection and able to provide some information on the planet here. So we start to have a relatively unbiased view. Okay, not for a very long period, because Kepler has the same difficulties for a long period, but Kepler do not have the same difficulty with very low mass planet here. So we start to have a relatively, and the best estimation we have for the probability to have one Earth-type planet in the habitable zone of stars is from 10 to 50%. But okay, you see the error bar is huge.
In one of the very first slides, you have been showing the accretion disk around forming stars.
Yes.
Is this true for second generation stars, or do you also have that for protostars in the very early universe?
Okay, I'm not sure I understand. Okay, you have
so
this.
You need to have had the supernova before.
Yes. Okay. I have to give the background of this. In 92, so 3 years before 51 Peg, Alex Volkshan has discovered first 2 planets, and then after a third one, orbiting a neutron star. And the eccentricity of the orbit is almost 0. It's absolutely a perfect circle. So for the formation of the neutron stars, you have lost maybe at least half of the mass of the star. So, if you have a dynamical system with a planetary system and you decrease the mass by a factor of 2, you will not finish with perfect circular orbits. So we are absolutely certain that the 3 planets orbiting the pulsar are of second generation. So the net result that you have to understand how to produce a different kind of accretion disk. And you have different scenarios to form this. One possibility is the fact that at the time of the explosion, part of the matter evidently went out, but part of the matter go down and form the accretion disk. So this is the reason why we are speaking about planetary system of second generation. So it's a completely different story, but for me, what is very interesting in this observation is the fact that it proves that if you have a good condition, you form planets. You see that it's a very crazy environment, and nevertheless you form planets.
Thank you, but not just to continue on these planets that can have life on planets. Is a second generation star with a planetary system good enough for the new 3, 4, or 5 generations in order to have chemistry that is rich enough to evolve?
Yes, but I don't know if it's very agreeable to be so close of a pulsar. Okay, I'm not specialist, but I don't know if the condition of habitability have been studied on the surface of this kind of planet. I don't know. At least one is 25 days, because the pulsar has a strong magnetosphere with a period of 600 rotation per second. I don't know. I have no idea. But what is very strange, because when Alex Volkmann announced this system with the 2 first planets, it was the worst moment to do some kind of announcement. Because 6 months before, another radio astronomer discovered an object with 6 months of period. And 6 months after, he went to a conference. He was invited to give a talk, and he was very gentleman. And when he arrived, he said, "Sorry, it was a mistake. It was a very complicated mistake. It was a very small error in the coordinate of the star, of the pulsar, and this induced the correction of the Earth's motion creates this apparent change of the timing." And at the same conference, Alex Volkmann arrived with 2 planets. And evidently everybody say, okay, wait 6 months. But in fact, after it was proved to be correct, because it was the quality of the measurement was so exceptional that you have a small interaction between the two planets, because the period of one is 60 days, the other one is 90 days, so it's a resonance system, so you can detect the change of the period due to the interaction, and this was absolutely proof that it is planets. No, it's a beautiful system.
Further questions?
Yeah, I have a question with respect to the TRAPPIST-1 light curve that you showed.
Okay.
The light curve of the TRAPPIST-1 system shows 2 peaks, at least 2, and I've never seen an explanation for those.
Oh. You mentioned 2 peaks.
Yep.
No.
Yeah.
on what figure? Here?
No, on the upper curve, it's in about 60-70% to the right. Yeah, there. And there's a second one on the lower curve, somewhere in the middle.
Here you have 3 planets.
No. I'm talking about the
here.
The peak, yes, not the dips.
Okay, sorry, I don't know.
Because my suspicion would be some detection effect, but
yes, I believe it's
because both peaks are asymmetric.
Yes, I don't know enough the details of, because this is combined curve of different instruments. I don't know what could be the explanation of that. I don't know.
The alien signal. Further questions, comments? There's one.
Maybe we can add that this kind of measurement will be used to try to detect moons, because the sensitivity, for example, in the solar system, the relative size between the moon and the Earth is only a factor 3. So if you have some similar situation, in fact, we have the capability to detect satellites.
Is not important the presence of magnetic field in a planet for life?
Didn't understand because the door.
Yes.
Can you repeat it?
The presence of magnetic field, in my view, is also important for life in a planet. For us, for example, it's a shield. Without a magnetic field, we would be here.
Yes, it's the reason why when I say the notion of habitability is probably much more complex. It's not only the temperature, but it's also the mass of the planet is absolutely critical, because if the mass is too small, it's very simple. The atmosphere will escape because it will not be retained by the gravity of the planet. And then after you mentioned the magnetic field, maybe, I'm not sure it's so important, but also you have plate tectonics. For example, on the Earth, the plate tectonic is absolutely a crucial phenomena, because if the luminosity of the sun increase a lot, because at the beginning, the luminosity of the sun was about 1/3 or 40% of the present luminosity. So, and then at the beginning, we have a huge amount, 95% of the atmosphere was carbon dioxide. So this very high percentage of carbon dioxide compensate for the small flux of the sun. So the temperature was not too bad. But then after you have the U-ray chemical reaction, so we have a strong decrease of the percentage of carbon dioxide. In about 1 billion years, it almost disappears. But at the time, the luminosity of the sun has not increased enough to compensate. So the story of life could stop at this moment. But happily, you have the plate tectonics. And so you re-inject always a small amount of carbon dioxide. And this is still the case here. Okay, people right now give a lot of comments and critics on carbon dioxide, but if we are here, it's only because carbon dioxide maintains the temperature of the Earth at some good level. So you see, it's the reason why I say you have a huge amount of constraints or conditions. And then after, but I believe if you have all this good situation, okay, life could emerge or not. And the only way is just to measure. We have no way to predict if what will be the probability to have life development. After you can have your own feeling. A lot of people give, oh, I'm sure that life should exist. Okay, okay, but it's not science.
Plus the sterilization effect of supernovas.
Yes, also, yes.
Neighborhood, yeah. There was another question.
There can also be other forms of life that do not depend on water or carbon dioxide.
I cannot say no, but okay. What is life? I believe we have to start from this point. Life, it's a phenomena where you have a small chemical machine, tool, able to interact with the medium, to protect themselves from the environment, and what is more important, to transfer all this information related to this process to her daughter. And evidently, what is the transmission? It's the genetic code. Okay. So, and what we know that if it's too cold, okay, chemistry is very slow. If it's too hot, the DNA will break. And the domain where you have interesting things for the chemistry, it's only a problem of chemistry. It's almost between minus 15 centigrade to plus 140 or 230. So, and this is almost the domain of liquid water. So the constraint to have liquid water is not anthropomorphic. It's really a problem of chemistry. If you need to transfer information from one generation to another one, you need to be in this domain of, okay, after you can dream to some completely unusual things, but Fred Hoyle imagined life in the electromagnetic activity in clouds and things like this, okay. But if we stay a little bit closer to maybe what could exist, in fact, the condition of temperature is very constraining. And okay, if you are looking at the interstellar medium, you have a lot of molecules. 90% or more are based on the carbon chemistry. Only a few very simple molecules are based on silicium. So apparently, a chemistry based on carbon is mandatory. So 30 or 40 years ago, people was exploring different possibility of different kind of life, and presently people are more focused on okay, we do not claim that every detail should be the same. For example, we do not know if with the DNA is the only way to do it. Because, for example, you have some chemists able to produce some kind of different kind of molecules with the capability to replicate. So the topology of DNA is not absolutely unique. And nobody knows, evidently, if nature will choose only this process or could have another one. But you have some basic rules. And for example, this problem of transfer of information, I believe, is a huge constraint. And after you have a liquid water, okay, after the water is favorized enormously the chemistry. It's a solvent. It's a very important solvent.
It made a point of discussion here. That refers to life as a sort of originally in a natural way from some chemical environment. But this might be just a small fraction of the possible life. For example, in 1 million years here, life form might not be based on carbon, but on nanorobots and silicon chips or whatever. So for these kind of life forms, I mean, all these constraints don't apply.
Sorry,
I
believe I have a mix between the micro and...
sorry. No, what I meant is these kind of conditions for life are, in a way, conditions for a natural evolution of life out of some soup. But the generic form of life might be artificial in the universe. independent of any constraints. I mean, I don't think that in 1 million years the predominant life form will be based on carbons here, but on silicon chips or whatever.
Wow. Okay. What is extremely exciting is that, okay, I speak about exoplanet because I'm more linked to exoplanet. But in some sense, what is the most interesting development is what we can expect from the solar system exploration. Because 3 billion years ago, the condition on Mars was quite good. So you have atmosphere, you have liquid water, you have everything of kind of chemical components. We still have all this proof of this period here. And, okay, today, no way, you have no life at the surface. But we knew that we have some volcanic activity in the past. So we have got a lot of heat inside the rocks. You have faults, you have liquid water, you have water underground. So I'm absolutely sure that you have liquid water at good temperature at some depths in the ground of Mars. All the good conditions for life development exist. And if life has started 3 billion years ago, nobody could claim that all the form of life disappeared on Mars today. In the rocks of the Earth, you have some faults at a very deep interior of the Earth. You have some unicellular form of life, living form of life. So nobody can claim that we do not have active life on Mars, but not on the surface, evidently. And then after you have this beautiful discoveries of Europa. Europa is a satellite of Jupiter. And 20 or 30 years ago, Voyager spacecraft took some picture of that and have detected an ice shield. So you have liquid water under ice. What is the reason why you have liquid water so far from the sun? It's because the tidal heating, because you have several satellites. They are on elliptic orbits. So always the shape of the satellite is obliged to be in agreement with gravity of Jupiter. So you have a tidal heating of Europa. It's enough to have liquid water under the shield. So what happened inside? Nobody knows. So this is typically one example. Another one is Enceladus. Enceladus is a big satellite of Saturn, and also with an ice shield and with some geyser, huge geyser of liquid water discovered also a few years ago. And more. You have several possibilities of life development in the solar system. So why, personally, I would claim that it's maybe more exciting. Let's imagine you have the money and the technology to send a spacecraft to analyze the ice on Europa. No need to drill the ice shield, because if you have several kilometers of ice, no way to do it. But you don't need, because due to the change of the shape of Europa, you have some break, and some water is coming from below and create some excess on some lines. So you only need to send a spacecraft, pick 1 cubic meter of ice along the break, and see, to melt this water, this ice, and see if you have something interesting inside. So, and you have a lot of space mission planned for 20, 30 years from now to do this. So, why I'm more excited by this? that, okay, if you are observing exoplanet, you see it's not so sexy. You have a small ozone line, you have things like this. Okay, after you are a little bit frustrated. But if you can see some living, simple, very simple organism coming from below the water of Europa, you can analyze the DNA and things like this. And if the DNA is not the same as here, it will be fantastic. You have the proof that you have two different origins of life. So probably it's one of the most exciting development. Okay, it's parallel to extrasolar planet, because extrasolar planet you can have the probability of and the proof that life exists. But in the solar system, maybe you have more promising of exciting development.
Final question.
In the solar system, the planets of the solar system, can we not look at for the presence of the higher molecules without going there? Can we look at their spectrum and analyze it?
To look on molecules on where?
Like the Europa or Mars, do we have to go there?
Yeah, no, because you have nothing. No, we cannot do spectroscopy to see. No, because you have to go and analyze, because you have not the equivalent of an atmosphere. You cannot do at distance. I'm not sure I understood what your question.
No, I'm just saying that from a distance, can we not know what are the materials in a planet without going there? We don't have such instruments.
I have some difficulty. So.
Yeah, I think you asked whether there are some remote sensing possibilities to analyze the content of the water, the buried water, or something like that.
No.
Okay, I think we thank Michel for the beautiful talk and the interesting information.
Merci.